Hello everyone, this is Xinyao Yu. It's my honor to present our paper PerSiVal on body AR visualization of biomechanical arm simulations on behalf of our team at University of Stuttgart and JP Morgan. In the past, biomechanical simulation and visualization were traditionally confined to the high-performance computing and professional settings. However, with rapid advancements in simulation techniques, fast, real-time biomechanical simulation has become possible. To harness this potential, we assembled a team of researchers from three disciplines: biomechanical simulation, distributed systems, and visualization. This collaboration led to the concept of pervasive simulation and visualization, or PerSiVal for short. So far, we have successfully implemented lightweight biomechanical simulations on mobile devices, such as smartphones. While these advancements have opened the door of biomechanical simulation to a broader audience, the users, especially the non-experts, may lack the domain-specific expertise necessary to effectively interpret and understand the biomechanical visualizations. To address this, we propose to render the arm muscle simulation directly on the arm using augmented reality, that is, leveraging the spatial alignment to foster a more immersive and engaging learning experience. Therefore, we propose a pipeline to enable the complete biomechanical simulation and visualization. In this pipeline, the biomechanical simulation will output the muscle activation level and muscle geometry with the movement data of subject as the input. The simulation data is encoded as the muscle colors, diagrams, and text, and subsequently rendered on the arm representation. Initially, the arm representation could be a static model, but our ultimate goal is to achieve a highly realistic rendering based on simulated muscle geometry. Within this framework, we propose 5 design choices: motion captured AR display, arm representation, perspective, and data encoding. Over the past 5 years, we have developed 6 prototypes to explore the technical feasibility of this pipeline. We developed our first prototype in 2019 based on HoloLens 1, where we situated referral markers on the shoulder, elbow, and wrist to provide motion capture data. In this prototype, the muscle activation levels were reflected by the color shades on related muscles. We then upgraded this on 2021 with HoloLens 2 and AR Toolkit. In 2022, our attention shifted to the use case of physiotherapy. We developed a prototype 3 for patients using a magic mirror AR setup based on a TV screen and Azure Kinect. We also developed a prototype 4 for physiotherapists using HoloLens 2 and OptiTrack. For prototype 3, we applied diminished reality to remove the real arm from the video streaming to reduce distraction in the view. For prototype 4, we rendered the arm drawing angles as colorful arcs around the subjects to offer visual guidance for physiotherapy movement. With the introduction of the Apple iPad Pro with the M1 chip, we finally have the opportunity to integrate motion capture, realistic biomechanical simulation, on-body visualization on the same AR device in the real time. This time, prototype 5 is able to run biomechanical simulation to calculate the muscle geometry on iPad Pro and then directly render it using video see-through AR. For muscle models, we upgraded prototype 5 to prototype 6. While in this prototype, we additionally offered a particle rendering style to reduce the amount of computation on the device and improve real-time performance. For the past 5 years, we collected feedback from over 70 participants in outreach activities, demos, and discussions, and we are going to reflect our lessons learned in terms of our design choices. We have tried 3 different motion capture strategies in our technical exploration. In the world, there's always a trade-off between accuracy, comfort, pervasiveness, and time latency. In terms of display and perspective, we have tried third-person and mirror perspectives. Our attempt to the first-person perspective did not satisfy our expectations due to the limited field of view of the mainstreaming AR head-mounted display. We succeeded in rendering high realistic arm muscles in prototype 5, but many non-expert participants expressed discomfort and fear about it. For data encoding, we encoded muscle activation level into color of muscles rendered on the subject's arm, and also into around body diagrams and text. The former caught more attention from the users as it coincides with muscle deformations. More detail can be found in our paper and supplemental videos. Thank you.